Welcome to podcast number 2, which is all about rate constants and the order of reactions. So this is going to be then our foray into a little bit of looking at the math that's going to go into working with these rates of reactions. So let's say that we go back and we think about our dinitrogen pentoxide that we had in podcast 1 and that decomposition reaction. All right, so if we have that decomposition reaction, if we plot the rate of our reaction versus its concentration, all right, well, remember that as we increase the concentration of our reactant, and in this case, our reactant was our N2O5, as we increase the concentration of that, we increase the rate of our reaction as well. And if we do this, we actually get a linear plot in this case. All right, and so what we can find then is that we're going to say that the rate of our reaction is equal to, all right, some constant. All right, and if we have a constant in chemistry, and it's not one of our major defined constants, we usually give it the symbol of K. All right, now this is a constant, but it's not a constant like the gas law constant, where that is, 0.0821 liter atmospheres per mole Kelvin for all gases. This is a constant that is specific for this reaction itself. All right, and so we're going to call this lowercase k a rate constant for this reaction. And so notice its rate is equal to k times our concentration of our N2O5. All right, so that's the concentration of the reactant in this case. The next thing that we need to think about is something that we're going to call the order of our reaction. In order for us to determine the order of a reaction, we have to run an experiment. And so when we run an experiment, we're going to get some data out of that. And we're going to do that, and we're going to do that calculation on slides 16 and 17. This one happens to be number 13, so it's coming up here before the end of this podcast. We're going to do this mathematically. We're going to see what happens. All right, but in general, right here we have A going to products. So notice that in our case, we had our N2O5 was producing our two NO2s plus our half of an oxygen, right? So that was our A producing products. And then we had the rate was equal to K times the concentration of our N2O5, right? Which was pretty much this here. Okay, so notice that the new thing in here is this M. Right, and M is the order of our reaction. And in the one that we had there is our example. Notice that our M, there's no number there, so our M has to be 1. Right? It's implied 1. Now, we would figure that out by running an experiment. We can't find that from our balanced chemical equation. Right? It says not from our balanced chemical equations. It is tempting to put in what the coefficient is from the balanced chemical equation, but that is not necessarily what that order of reaction is going to be. We have to run an experiment to determine that. Well, if we know the order of a reaction, then we can work backwards and calculate the rate constant, because we'll probably know a concentration, we'll know an order, and we'll know a rate. We're going to use this soon. All right. Now, the biggest thing on this slide is this stuff. This is important. Are the units, all right? Because our units can help us determine the order of our reaction. All right, so let's write a generic thing where we have rate is equal to K times A. All right, and we know that that's raised to some power, M, right? That is the order. All right, well, this says that rate is always in moles over liters times time. Okay, well, I am looking for the units of K right now. All right, so let's say that I have K here. And I don't know what the units of that are, but it is times A. All right, and A is in brackets, and that means that that is a molarity. So that means that we're going to have moles over liters. All right, if this reaction were first order, right, then M is equal to 1. So I'm going to put 1 up there. Right, and so the units of K must have units of 1 over time. It's the only way that both both sides of our equal sign can have the same units. All right, what if we did this for one other one, but I'm just going to do, what if we had that rate is equal to K times A. Let's say that this was second order. Okay, again, rate is always moles over liters times time. We're looking for the units of K, and A is still moles over liters, but notice that it's second order, so we're going to square these two things. Well, the only way that I can get the units to be the same on both sides is if the units of K are liters over moles times time. So second order, K has units of that. First order, K has units of 1 over time. Right? And we could actually do this for any possible order. I need you to know the units of K for first order, what we call 0th order, and second order. All right, well, 0th order would be where we had rate is equal to K times A to the 0 power. Well, remember, anything to the 0 power is just 1 with no units. So really, that just is rate is equal to K. And so K would have units of moles over liters times time, by the way. You need to memorize those three if you can't work those three out. Well, obviously, we're not always going to have a reaction like our N2O5 decomposing. Sometimes we're going to have multiple reactants. And if we have multiple reactants, like A and B coming together to form products, then the rate has to be equal to, well, it's based upon both of those reactants. So rate's equal to K times the concentration of A, raised to some power, that's its order, times the concentration of B raised to some power that we're now calling N, that's its order. All right, and so in this case, we actually have 3 different orders. We have the order of our reaction with respect to A, that's the M. We have the order of our reaction with respect to B, that was the N. And then we have the overall order for the reaction, which is just the sum of those, M plus N. Right? And again, it says that the orders can be determined the same way they are for single reactants. We are getting really close to calculating those, right? But again, that just means that we have to run an experiment in order to do these. Here we have a sample problem. A reaction has 2 reactants, X and Y. What is the order with respect to each reactant and the overall order of reaction? So, right, rate is equal to K times, all right, X to the second power and Y to the first power. So it is second order with respect to x. It's first order with respect to y. Right? And then it is third order overall. Note, orders can be anything. Right? We're going to focus on 0, first and second order most of the time. But you could have a 1.1 order. Heck, you could have a negative 10.7 order. Right? You could have like any of these things. Right? It does not have to be 0, first and second. Those are just the main ones that we're going to focus on. But just note that they can be anything. They can be anything with respect to each one of the individual reactants. They can be anything for the overall as well. So now let's find the order of reactions by using some data that was collected experimentally. So in this case, we have A plus 3B is going to 2C. All right, notice that we have run 3 different trial runs, right? We have varied concentrations of A and B, and then determine the initial rate of the reaction. So it says, first off, what is the order of the reaction with respect to A? All right, so what we want to do is we are going to find when A changes, but B is constant. All right, so what we're going to do is we're going to look for 2 different places of data where that happens. All right, so we need A to change and yet B to remain constant. So I'm going to pick these 2 sets of data here to run this one. Okay, and I'm going to show the entire thing for this one, and then we're going to shorthand it for the second one there with respect to B a little bit later on. All right, but I'm going to show why we're picking this. Okay, so we know that rate for this is equal to, all right, K times A to some power, we're going to call M, times B to some power, that is N. All right, K is going to be a constant for this reaction, so mathematically right now we are going to ignore it. So what we're going to do is we're going to say, okay, rate, what if I write those 2 rates as a ratio of each other? And I'm going to write them as the bigger one over the smaller one. So I'm going to have 2.73 times 10 to the minus second divided by 1.36 times 10 to the minus second. All right, so this is the rate. All right, that is going to be equal to, all right, so A to some power. So again, I'm going to do A as a ratio. All right, well, since I chose 2.73 to be on top, I'm going to choose 0.420 to be on top. I got to stick with the same line. Raised to the M. All right, times B raised to N. So that's going to be 0.300 divided by 0.300 raised to N. All right, well, the reason that I chose it where B is constant is because this then just becomes 1. And so the whole thing is going to simplify to be 2.73 times 10 to the minus second divided by 1.36 times 10 to the minus second is equal to 0.420 divided by 0.210 raised to the M power. So if I calculate this out, this is going to be 2 is equal to 2 to the m power. So thus m has to equal 1. All right, next one says, what is the order with respect to b? So in that case, right, I want when b changes, but a is constant. So instead now, we're going to pick the top two sets of data. All right, and I'm not going to write it all out because I know that the a's are going to just become 1. And so what I'm going to do is I'm going to write the rate, all right, the ratio of the rate, so 1.36 times 10 to the minus second divided by 3.41 times 10 to the minus third. Right, those are the ratios of the rates. And again, I'm just writing you can write the smaller value on top of the bigger one. I just do it this way because I end up usually with whole numbers, and that's a heck of a lot easier to work with. All right, is equal to, all right, so our 0.300 divided by our 0.150 raised to some power n. So this is 4 is equal to 2 raised to some power n. And so n is equal to 2 in this case, right? Note that the coefficient for b was 3, not 2. You can't just use the coefficients. You actually have to work these out to solve for them. Continuing on with this problem, it asks us to calculate the overall rate expression. All right, so what they want then is they want rate is equal to k times, all right, a, and we found that a was raised to the first power, right, because it was first order, times b, and we found that it was second order. So that is all that they're asking for in that part. If we move down, calculate the rate constant, including units. Okay. We can choose any line of data and plug in to what we found to be the overall rate expression. All right, so I am going to choose the top line of data. So the rate, if we look way over on the right, the top line of data was 3.41 times 10 to the minus third. All right, and remember that rates have units of moles over liters times time. All right, that's equal to K. That's what we're looking for. All right, and then we have A. All right, well, A for that one was 0.21 moles over liters times our B, which was 0.150 moles over liters, and that is squared. All right, well, solving for the value of K is really easy. We can just do the math on that, right? And if we do that math, the algebra, 3.41 times 10 to the minus third divided by 0.21 divided by 0.150 squared, we're going to get that K is equal to 0.722. All right, but the units. All right, well, on the left-hand side, I had moles over liters times time. On the right-hand side, I have K, and then I have moles over liters times moles squared over liters squared. Well, this is moles cubed over liters cubed. So K, in order to have the right units on both sides, K, well, we know we need time on the bottom. All right, I need 1 liter on the bottom. I currently have 3, so I need 2 liters on top of my K to cancel those out. And then vice versa, I have 1 mole on the top. I currently have 3, so I need moles squared. So this would be 0.722 liters squared over moles squared times time. All right, so that ends another podcast. On our next one, we're going to look at, first order reactions themselves more in depth. We're going to look at them alone.